So now I can get into some new protocols which are called data center bridging protocols. Now still I'm not going to talk about the virtualization, but there are several protocols that have been done very recently, and you can see the dates here. 2010 and 2011. These protocols have been done specifically for data center bridging. 4 of them. And actually these are mostly for storage traffic. Storage traffic has one characteristic, which is that you cannot drop it. If you drop it, it is really bad. If you read a disk and you get a read error, you get worried. So we are not used to seeing read errors or write errors or any disk errors. The day I get a read error, I start thinking of changing the disk, basically buying a new disk, which is few $100 thing, right? So the idea is that we are not used to just getting an error like that in the storage. On the network, we get the error every day. Every day I get packet lost, too delayed, something, congested, can't reach the host. That is every minute thing, right? But on the disk storage, we don't do that. So they had to change Ethernet so that it doesn't lose any packets, actually to be exact frames. The losing packet depends upon transport layer, you mean by TCP.
Yeah, TCP or UDP.
Yeah, so the thing is, TCP is not good enough for data center. First of all, in data center, we don't even want to go to TCP. We don't even want to go to IP. Right? So I want to be able to read my disk using plain Ethernet. And there are cases, we have a module on storage by itself where we will talk about, you need IP, but in many cases you really don't want to go higher layer. Right now, when you read your disk, you don't go through any protocol. You just have a SCSI in your computer and you just connect it like that, right? There is no protocol, no IP, no TCP. You read your disk, right? Like that. And so that's what we want to kind of keep is in the data centers. Actually, I'm sorry that I don't want to go into storage right now because we have this data center bridging to discuss. And storage is the next module, which is where we'll talk about fiber channel, which is what you don't use at home, but fiber channel is what is used in the data centers. And it has certain things. And one of the things it has is it doesn't lose packets. So anyway, 4 standards: priority-based flow control, enhanced transmission, congestion control, and data center bridging exchange. And I'm going to just go one by one. So flow control is easy. Basically, in the old days, Ethernet had a frame called page frame. When a switch sent a page frame to somebody else, that switch basically blocked that port. Means it will not send any more traffic on that port until that page expired or it got that okay, something like that. Basically, page has a time field which says, please don't send me anything for 1 second. If I send you a page frame which says, please don't send me anything for 0 second, that means you can send. Alright? That means don't pause anymore. So the same page frame basically will come back, or it will say, time may expire, one of the two. Until then, you don't send anything because it will be dropped. It was defined in 1997. This is what we call on-off flow control. You can turn on the flow, you can turn off the flow. And the frame actually just a little bit detailed. That is not a unicast frame. You just don't tell the neighbor. You just send a broadcast frame, so you don't really have time to figure out who your neighbor is. You just send it to this address, and since it's a multicast address, anybody who listens to that multicast address will work on it. The another new thing about this is that this is not forwarded. So this page frame, even though it is a multicast frame, it is not forwarded. All the multicast frames are forwarded. But the main problem is it stops all traffic, and therefore very soon this will back up. Its buffer will fill up, and it will have to tell the other guys, please stop, and they will tell the other guys, they will stop other guys. So congestion is in Kansas City, but all the traffic in St. Louis is congested now. Why? Because there is a back pressure. Because there are two problems. One is the back pressure, second is that all traffic. So they fixed it. They fixed it by putting priority-based flow control. So now each priority can be stopped individually. So you have priority 0, 1, 2, 3, 7. You can say, please don't send me anything priority 1. Now the priority is not really a priority. You might be able to send 0 but not 1. Now 1 is higher priority, right? But no longer. Now priority is just like a class. Don't send me anything with that bit being equal to 1. That's 3 bits. Right? So you can individually block any priority you want. Priority 1 blocking does not mean the priority 0 will stop. So if you want to block all priorities, you just block all. If you want to start everything up to 4, just send 4 frames, 0, 1, 2, 3, 4. Priority based flow control. That's all there is. Alright? And obviously the pause frame as before has a time to live, and so up to that time you don't send. After that you can send, or if you get another pause with the 0 time to live, you can send. Alright, so one thing is, with this, at least the high priority can continue, the low priority can back up or can be dropped, if you want to call it that way. It's up to you to decide what can continue or what should be dropped. The next thing is enhanced transmission selection. Second thing, there were no guarantees before, and people wanted guarantees for the storage traffic. They wanted to say that, well, I want to make sure that I have 75 megabit available for storage. Otherwise, my storage is will not work. So they created that by enhanced transmission selection. Here, what we do is you take these. Now we don't call them priority. We have classes 0 through 7. And then you can group them. So you can say group 1 is these classes, group 2 is this classes, and group 3 is this classes. And so the classes are what is marked in the frame, and the group is what we want to manage. So we just want to manage 3 groups or maybe 2 groups, maybe 5 groups. I don't know. It doesn't matter. The number doesn't matter. But really, you group them, and then you say, I want to have at least, out of my gigabit, I want to have at least, let's say, gigabit. So I want to have at least 100 megabit for group 1, or maybe 500 megabit for group 1. Okay, and I want to have minimum of 10 megabit for the group 2, and I want to have minimum of 10 megabit for group 3. So you can allocate some guarantees bandwidth, except the rule is that you cannot allocate more than 75%. So the 25% has to be left for the best effort, for something that is not reserved. Up to 75% can be guaranteed, can be allocated to be exact. And the second rule is that if somebody doesn't use their allocation, other people can use it still. So if I say, well, I want to have my 500 megabit for group 1, but there is no group 1 packet in my queue, group 2 and 3 can go. Unless nothing is wasted. Alright, with those 2 rules, the rules are traffic is divided into classes are grouped, then the fairness within a group. So now here is an example that if you have a group and there are some queue here, there is some queue here, there is some queue here, there is a fairness, round robin. So you don't want to send all the packets of one queue in that group. Okay, now fairness is itself a lecture and I would not go through that. Anyway, so the fairness has many ways. Okay, fairness could be, max min fairness is one example, but there are many other ways of fairness. So I would not go into that one. But so you will be fair among these 3 queues, and this will be fair among those 2 queues. So fairness within a group, 3 to 8 classes, and at least 3 classes generally are recommended. So one is with PFC. So one is the class with PFC, which is the priority based flow control, and one without the PFC, and one is strict priority. So they would have 3 groups. This one will have a strict priority, this one will have the one with a PFC, without PFC, whatever. But basically you can make as many classes as you want. This is just sample. And bandwidth is allocated per class group, and bandwidth unused by a group is used by others. So here is an example. So suppose we have 3 groups, and we say group 3 gets 3 units, and group 2 gets 5 units. So here is an example. Group 3 gets 3 units, group 2 gets 5 units, and group 1 gets no reservation, right? And let's say they send 2, 2, 2, 1. If they send 2, 2, 1, they will all get through 2, 2, 1 because everybody is sending below their reservation, and there is nobody else to use the leftover anyway. But if they send 3, 5 and 3, so this will, group 3 has 3, so they will get 3. This one has 5 to send, but its reservation is 5, so it will get through. And this one sends 3, this will only get 2 because total is 10. So 3 plus 5, 8 plus 2, 10. The whole link is used. So they will, even though they send 3, they will get only 2 because that fills up the capacity. Now let's take the third example, third second. They send 4, 6 and 2. So 4 will get 3, guaranteed. 6 will get 5, right? So now there is 2 and 1, right? So basically this one gets 2. Actually this is already overloaded. So basically they get 2 and these get their capacity maximum. Okay? Actually it would be better if I had another example here, which I will add later on, where these two don't use their resources and the link is not overloaded, then they can get something more than the reservation. So for example, this should be able to get more than 5. We don't have an example here. But they would get more than 5 if, let's say, the first group was not using anything. Right? So that is the thing, is that anything not used by everybody. Yeah, that's what basically it is that per application, each application decides which priority, what packet will go into what priority. Basically, for data centers, you have multiple classes. Now we are using the word classes, not priorities. That is one important difference, because previously the word priority was much more strict. That meant you couldn't really transmit priority 6 if there is some any priority 7 traffic. Now this is all gone. Now we have classes. And the classes are grouped because you don't want to manage 8 different policies, so you have 2 or 3 policies. So first policy group consists of these, second policy group is this, and third policy group, and you could have 4, 5, 6, as many as you want. You could have 8 groups. For each group you have some reservation, maybe not be for each group, for some of the groups you have some reservations. So here in this example we have 3 groups, and for group 3 we have reservation of 3, and for group 2 we have reservation of 5. And let's assume these are all in just to be a little bit closer to the reality, is in gigabits. 3 gigabits and 5 gigabit, total link is 10 gigabit. Alright, so if this is the traffic sent and this is the traffic transmitted, the sent traffic in the first time interval, group 3 sent 2, group 2 sent 2, and group 1 sent 1. The link is underloaded, there is no question. Everybody gets whatever they want. So everybody gets 2, 2, 1 on this side. In the second time interval, they sent 3, 5 and 3. This is guaranteed 3, nothing is left over. This is guaranteed 5, nothing is left over. This is basically 3 and 5 is 8. So only 2 can get through. This is not guaranteed anything, but 2 will get through. So this is the allocation. In the third part, we have total demand of 12. This one demands 4, this one demands 6, and this one demands 2. So this one gets 3 because that is guaranteed. This one gets 5, that is guaranteed. They get 2. And then they don't get any more than whatever they had reserved. If this 2 would not be there, if there was no traffic here, then maybe they will get. Okay? So while we want to give the best effort, this is actually the best effort traffic, some minimum, because we don't want to make it 0 because all the connections will break. Even if they're best effort, they will break. TCP connections will break. So we give them 2, and then and since the link is overloaded, nobody else got more than what they reserved. If the link was underloaded, then they could get more than what they reserved. Let's say if nobody asked for anything, this guy asked for 9, they will get 9. 3, 7 and 3. That's a drawing error.
Okay.
I did not draw it correctly. I mean, I drew it all this and then I forgot probably to make it 4. PFC stands for Priority Based Flow Control. strict priority comes from the old days. Original Ethernet had strict priority. Not original Ethernet. Original Ethernet had nothing. But when we came to 802.1q, which is the VLAN, in the VLAN we put 3 bits for priority. Those were strict at that time. And so a lot of priorities got starved. You know what that means, right? The lowest priority got starved and they really couldn't use the network that much because somebody else will come in and they would be last in the queue. And so that was not a good idea. Strict priority was not a good idea. So now they have come to what we call classes. Classes have no connotation of being higher or lower. You know, I mean, like you have a black class and white class. We don't say that one class is higher than the other class. See what I mean? So priorities are different than the classes. Classes have no higher and lower understanding, right? So now we have 8 classes. But since they are called priorities, so the thing is, so PFC was priority based flow control. What that did was the PAS, which was for all priorities. Previously, PAS was just, when the PAS was introduced, PAS was probably not there in the original Ethernet either. So whenever the PAS was introduced, they said everything will stop. And that broke everything. Right? They think that was not a good idea. They said we can stop something, but not everything. So now that is what priority based flow control is. You could start one priority, priority 5. So the last thing they added is quantized congestion notification, QCN. And believe it or not, we worked very hard to get our scheme in. We fought with QCN. The story about QCN is we had done some original work on something called ECN, explicit congestion notification, which is now part of the IP standards and it is used in the IP. Somebody called me from IEEE and said, why don't we apply that to Ethernet? And I went there and said, no, this is too old. We did that work in 1986, and now, with high-speed networks, you really need, better schemes, this and that. So we did, quite a bit of work, but we lost. And some other professor took that bit stuff and finally made this scheme. They sort of won in the sense that political battle, this is a standard, but it is not being implemented, as you will see in a minute. So this is somewhat close to my heart thing, we spent 2 years on this. So this is QA2 2010 standard, dynamic congestion notification. And the way it works is that a switch, whenever its queues become big, it sends a source quench message to the source. What is source quench? Source quench message is not pause, but it tells the switch that please stop, I am in trouble. Okay, so it just notices whichever packet happens to be coming in, hopefully it is random, and says, look, the queue is too big, you are coming in at the wrong time, please reduce yourself. And there is some probability associated there too. You just don't tell people coming in at the end that you are wrong. Maybe people who came in the front were wrong. So there is some probability with them, you admit them, or with some probability you reject them, or not reject them. Basically you send a source quench. Source quench goes all the way to the source. It doesn't stop at the intermediate switches. It goes all the way to the source. And then the source stops. Source stops means reduces its load. And then some time later it increases its load. Alright? So in the source quench, some first few bytes of the packet are sent. So the source can figure out which flow is it that is causing problem. Because source might be sending packets to 1,000 places. Not all of them are going to the congested area. But some went to the congested area, so it knows that, packets going to Germany are congested. So it will just stop those flows. Very simple. If your queues are long, you just send a source quench to the packets that are coming in, to the sources, and say please reduce, and the sources reduce. And the reason they had to put this in Ethernet is because something else that we are going to talk about later, Fiber Channel has this. Not source quench. They have a flow control, just like TCP IP, where not a single packet is lost. And people were not happy with Ethernet because packets were lost. So they said we want to make sure that Ethernet doesn't lose the packet, and therefore we want to put this standard. And so this scheme was selected for that reason. So now So this was selected. In our scheme, it was the opposite of this. Basically, in our scheme, what happened was that the switches would keep some kind of averaging on the queues. So you cannot just use the queues as they are. You really have to keep averaging. And then you send some signal to the sources, and the sources will reduce. And then when you want to increase, you send them increased signal. So that was a slightly different feedback, but it was different, right? So the reason our scheme lasts is because the standards are dominated by the switch people. These host people don't come to the standards for whatever reason. All hosts are made by Intel, probably one company. So they come to the standards actually, but switches are hundreds of companies making switches. I was told, look, we don't want to do anything complex. And we have 50 ports. And 50 ports means, we are not going to do 50 queues averaging this and that. So this is too complex. So this one basically what it did was it put the complexity to the source. The source is very complex. The switch is very simple. Now source has to remember that I sent a packet to Germany a second ago, and that flow has to be done. So it has to keep per flow state. And it has to reuse that flow and not everything else, right? So the story now is that it is implemented in all the switches, but it is not implemented in any host. The end result is you don't get any congestion control. However, marketing people are very happy because they can market and kill fiber channel, which they did. Basically that, we have the same feature that you have. All right, but in the real world, it was, and I was told that, look, we really don't really want to do anything. We just want to have a stamp that we have congestion control. And it doesn't matter. With that, I think I finished everything on QCN. Yeah, there's another problem with this scheme too, is that source may not be real source. Source may be a router, which is forwarding from some other Ethernet, right? And so if you tell them to start, they slow down, what are they going to do? They cannot slow down. They will just throw the packet which are coming in from this real source. They can slow down, but that will fill up the queues, right? So the only way congestion control works is when the real source stops. Because the real source can stop because it is keeping the packets on the disk and reading from the disk, it is reading some files and all that. So it can stop, but the routers cannot. Anything in between cannot. So that's another reason is that it does not really help. But anyway, it is done, final, and we are on business. And the professor who won actually made a few $100 million because he worked for a Cisco company. But having said all that, now the next thing they did was the DCBX. DCBX is Data Center Bridging Exchange. It's a great name for LLDP extension, right? LLDP is Link Layer Discovery Protocol. It's the neighbor discovery. So you find out what the neighbor knows, what language they speak, what feature they support. So they just figure out what features they speak so that we can speak the same features. That is LLDP. There is a very similar protocol which is called shortest path bridging, in which we send out messages to the whole world to figure out what is the shortest path. That is different. But LLDP is simply neighbor discovery. It's not the network path, right? You just want to find out whether you support 100 gigabit, 10 gigabit, full duplex, whatever, frame size. So finding that out is LLDP. So LLDP now is, you remember, LLDP is very straightforward protocol. It is extendable in the sense that they just say that you send out TLV. What is TLV? Yeah, type, length, and value. So you send out type, length, and value, and you can have as many as you want. So you could have 15 type, length, and values. But the types have to be standardized, because if you say I have type 15, so everybody has to know what type 15 means. So every time a new standard comes up, they describe what the new extensions are. So because we have this data center bridging, they have to specify the new TLVs. The new TLVs are priority group definition, what is the group bandwidth allocation, whether PFC is done or not, QCN is done or not, and things like that. So all these new features, whether the next guy supports or not, you have to find out. And that standard is called DCBX. Primary goal of DCBX so that we can implement what we call data center bridging, DCB, correctly. Otherwise, you wouldn't know whether I wouldn't know whether my neighbor support QCN or not, or whether the source supports QCN or not, right? And here's the thing. Suppose you want to do that previous thing we did, the priority allocation. If I don't know that this group gets 2 megabit, and then I may not send it that rate to you. Right? So we have to negotiate all that. So that is what it is. We negotiate the capabilities. And the word negotiation is used here rather than information, is that if somebody says, I want to give 3 megabits for something, you could say, no, I want to give only 2 megabits, and then, that will be settled by whatever rules have been set. Right? So that kind of negotiation is possible automatically for the machines to do. All right? These are the new TLVs that are specified in this standard. That brings us to the end of this lecture. Ethernet's use of IDs as addresses makes it very easy to move systems in the data center. That is the key point you learned. First is that the Ethernet addresses are IDs, and what addresses are locators? IP addresses are locators. So they are bad because every time you move, your address changes. Here your address remains the same, and that's very good. And so basically because of that, people don't want to go to IP layer, they just want to move VMs in the Ethernet layer. So the whole data center is one big Ethernet. Well, not really. I mean, you might have subnets, but you just move in one. Let me restate. So the whole data center may not be one big Ethernet. You generally move in one big Ethernet. You might have many big Ethernets in the data center, but you won't get out of the Ethernet into another, because that is a lot more work. Second message is that spanning tree, which was used to make it simple and stupid, is now really smart. Instead of that, we use a smart scheme, and those are the several smart things were done. First was rapid spanning tree, then multiple spanning tree, and then shortest path bridging. Shortest path bridging is just putting OSPF in layer 2. Slowly we start wondering why do we need IP in the first place? Because everything Ethernet is going to do. And the second thing is, what is Ethernet? Actually, the whole Ethernet previously was defined by CSMA-CD. There is no CSMA-CD anymore. So what is Ethernet? Ethernet is a frame format. As long as you send packets in this frame format, it is Ethernet, period. Ethernet is signaling. Ethernet is control plane, but not access anymore. Access is very straightforward. Everybody is line to line, point to point. So everybody speaks all the time. VLANs. Virtual LANs, they allow different non-trusting entities to share an Ethernet network. With VLANs, we can put many different departments of the same company into the same VLAN and and not have to worry about it because they will not see each other's broadcast. And then the data center bridging extensions, there are 4 of them, 4 or 5, I forget. But basically, let's go one by one. One was priority based flow control. There was enhanced transmission selection. Priority-based flow control simply said that you send pause and that stops only one priority. Enhanced transmission selection said that you can reserve bandwidth. QCN was another one. QCN simply did the congestion control. And the final thing was DCBX, which was extension to LLDP, so that we can exchange our capability. When you have point-to-point links, so what happens is basically we have 8 copper wires going, right? 4 on 4 I send to him, and on 4 he sends to me all the time. There is no access required.
So any detection,
there is no collision, there is no detection. The thing is, what you do have to detect is that when I'm sending, I'm framing it so that basically I send zeros all the time, and that means nothing. And when I start sending something, I send something different first in the beginning to make sure that a new frame is coming, and then they can start looking for the source address, destination address, all that. That is all Ethernet. Ethernet is framing. So there are 8 copper wires, 4 going this way, 4 going this way. Full duplex, yeah. So actually, that question is kind of a mute question, whether, if you got a 3 megabit guarantee, would you get a QCN? I suppose not, because I will know that you are part of this, and so that queue will, as long as you send only 3, you would not get a QCN. But if you suppose send 4, then you might get a QCN. So the question is, Spanning tree did cause a bottleneck because everything went through the root, or much of the traffic went through the root. Much of the traffic, not everything. Right? If you want to go from here to there, you have to go through the, whatever joining point is, which generally was the root for many things. So there was a bottleneck. With shortest path, remember we also said that we also have called ECMP, which is equal cost multipath. If there are two paths from source to the destination, you take 50% this one and 50% that one. So really, that is the best you do. So nobody takes anything longer than the shortest, but there could be multiple shortest path, which is very common in the data center. If you notice in the data center, the way we do it, everybody has 2 and 2 and 2 and 2. They're all equal cost. Right? So there are lots of equal cost paths. And so everything gets used much better. All right, with that we finish this lecture.